All right, welcome to Chapter 10, Part 2. In Part 2, we're going to talk about the second and third laws of thermodynamics. We just finished discussing entropy and how we could judge entropy based on how a system might change. And so now we're going to talk about some implications for spontaneous reactions. The second law of thermodynamics can be defined in a couple of ways, but the gist, the takeaway, is that the overall entropy change of the universe should be increasing for spontaneous processes. That means the overall universe, right? The system you're studying plus all of the surroundings, everything else in the universe, should have a net increase in entropy, right, for a spontaneous process. For spontaneous processes. Now, delta S of the universe, right, is going to be delta S of the system plus the change in entropy of the surroundings. So even if you have a system, a process that's getting more orderly, if the surroundings are going to have a much larger increase in entropy, they're going to be getting more disordered, then overall, you're still going to see delta S of the universe being positive, right? Increasing. So let's think about how we can relate that to converting heat into work. And then we're going to talk about a couple of specific systems. Now, the first law of thermodynamics tells us that energy cannot be created or destroyed, but it can be transferred or changed, right? Energy can be transformed from one type of thermal energy to mechanical energy, right? Can be transferred via heat or work. But something that we have to take into consideration is that it's impossible to convert heat completely to work. We always lose some. There's always this waste energy. Why is that? Well, when we think about what work is moving a mass in a direction against a force, right? It's an orderly movement in a specific direction. However, when we think about how energy is transferred due to heat, right, it is much more chaotic. How does heat transfer energy? Well, yes, heat in general overall is going to flow from an area where there is more heat to where there is less, right, to higher temperature, from higher temperature to lower. But how is that energy transferred? Well, heat flow, right, is that kinetic energy transfer when you have a collision, right? So between colliding molecules or atoms. Now, molecules, especially if we're talking about in liquids and in gases even more so, those molecules are moving in random directions. They're not all flowing in one straight line. So you wind up getting some collisions and transferring heat in a direction that you're not trying to, that's not going to be helpful. So you are always going to lose some energy there when you are trying to convert energy. Now, let's think about that in terms of a couple of specific applications. For whatever reason in this program, this page gets cut off, so I'm going to blow up this like white space up here at the top. We're going to look at two different applications here. We're going to come over here and discuss this polymerization reaction in just a minute, but I want to go even a little bit more simple. Let's think about water freezing to ice, right? This is going to be an exothermic process, right? Those water molecules are going to slow down and they're going to lose heat energy. Heat is going to flow out of that system, right? Because the ice is overall going to have less energy. But it's getting more orderly, right? Water is a liquid, ice is the solid form. There are going to be less microstates available because all of those water molecules are going to be stuck in place where they can vibrate, but they can't move past each other anymore. So this is going to have a negative delta S, right? Things are getting more orderly. But, right, it's exothermic. So heat is going into the surroundings. So what's happening to the surroundings? All of the molecules and particles outside of that system of water going to ice are going to increase in energy. And so while the system might have a negative delta S, might be getting more orderly, the surroundings are going to increase in entropy because they're taking on that extra heat, right? They're going to increase in temperature. If we look at this slide over here, where we are going from some number of monomers, right, to one polymer, this is another example of a spontaneous reaction, right? Water freezing to ice is a spontaneous reaction at certain temperatures. The number of monomers here is going to be greater than 1, and we're going to make one polymer, right? So fewer particles, there's going to be less microstates available, right? If there's less microstates available, then entropy is going to go down, right? But this is a spontaneous reaction at certain temperatures. So what you're going to see here on this slide, and which is hopefully going to be apparent to you here, is it's exothermic, right? So it can be balanced by this release of energy into the surroundings, right? So you wind up having that negative delta H that's going to balance out that negative delta S. Okay, so favors spontaneity, but we're going to come back to that. It's going to be at certain temperatures. That's going to be important. It's going to be, we're going to see that delta S is of the surroundings, right, is going to be related to delta H, whether it's endo or exothermic, and the temperature. The temperature is going to be really important here. All right, let's just jump past that. Now, the third law of thermodynamics. The third law tells us that the entropy of a perfect crystal of any pure substance is going to approach 0 as you get to absolute 0, right? 0 Kelvin. Delta S, just like delta H, is a state function, right? And what does that mean, a state function? It means independent of path, right? So it doesn't matter how we get from starting materials to products, right? Reactants to products, whether we go in some sort of straight line, whether we break everything down into the elements and then build it back up, whether we have 8,000 intermediate steps, right? The difference between where we started and where we finished is going to be the same no matter which path we take, right? So that's helpful for us, right? Because we can figure out delta S based on specific paths. And in this case, we're going to look at standard molar entropies, right? That's what's on this table. A standard molar entropy, it's a little bit different than like the heats of formation we looked at. You're never going to see standard entropy as 0 because what we're looking at here when we calculate standard molar entropy is the change in entropy of a substance from 0 Kelvin, where delta S would theoretically be, or where S would theoretically be 0, to 298 Kelvin, right? Some sort of normal temperature, about 25 degrees C. So those numbers have been tabulated. You see them for elements in their standard state as well as compounds. And of course, just like with enthalpy, it's important that you recognize the state does matter. Liquid water versus gaseous water is going to have a different molar enthalpy and molar entropy. They're all going to be a positive number because they're going from 0K of 0, where entropy is 0, to 298K is always going to be more chaotic, right, as we go up in temperature. So you'll notice these are all positive numbers. Now, when we go to calculate entropy changes in a reaction, and on the lecture notes that I gave you, you don't have these weird typos, so what I want you to do is just disregard this side of the screen and look at this right here. This reaction, or this equation, should look very familiar to you. Delta S of a system of interest is going to be the sum of delta S of the products minus the sum of the delta S of the reactants, right? Because it's a state function, we can look at the change in entropy of the reactants to the products, right? So it's like we're taking them all the way back to 0 and then bringing them back up to standard temperatures. It's a very simple equation, especially since you see it multiple times. And to solve just a sample problem here, we're going to look at the reaction of ethene and hydrogen to produce butane. Now, they're saying you're going to use the data from that table on the previous slide. You would always be given data for a problem like this. So it's an easy setup, right? We're going to start with our products. Now, what you should recognize again is I had some issues here. This X should be a plus sign, and this 4 should be an arrow. What a weird way to change. All right, so products, we only have the butane. And there's 1 mole of butane. We're using the stoichiometric coefficients times 310.03 joules per mole Kelvin. And then we're going to go ahead and subtract the reactants. And I'm going to come down here. That's going to be 2 times 219.5 because there are 2 moles of the ethene in our balanced equation. And to that, we're going to add 1 mole of H2, which is 130.6 joules per mole Kelvin. All right, now once we complete this, when we're going to look at the sign, we're going to find that the delta S of this reaction is negative 259.6. Now, would you have expected a negative delta S? What does that tell us here? A negative delta S means entropy is decreasing. This is getting more orderly. Well, look at the stoichiometric ratios. We have 2 and 1, so we have 3 moles on this side to 1 mole on the product side. There's going to be a lot less microstates for the product side where there's only 1 type of molecule. So yes, this sign makes sense for us and how we would judge that change in entropy. We're going to wrap up with Gibbs free energy in the third and final part of these notes. I will see you there.